So in this video we're going to look at a new way to measure angles. We have been measuring angles in degrees our whole lives probably. We're going to look at a new way, a better improved way of measuring angles called the radian. So here's the basic idea. Just like we had similar triangles, we can have similar figures. And we're looking for measurements that are invariant or constant. And the problem with degree measure is a rotation around a circle of 360 degrees is arbitrary. It's probably based on some of the early base 60 number systems and probably loosely based on the orbit of the planet Earth around the sun. It's a way of, degrees are a way of measuring angles that would not be constant across the universe. And what we really want is a way to measure angles that any developed civilization in any galaxy in our universe would be able to come up with. And so the idea is to take advantage of similar figures again. So for example, here's an angle theta. It's a central angle. It's the angle swept out through some arc, an arc BC. And we'll give this arc a name. We'll call it S. It's very customary in trig to give arc length, or in math in general, to give arc length the name S. So we have an angle BAC, which I've given the name theta. And we can see by the geometry that is here that the angle B prime AC prime is exactly the same angle as the angle BAC. So we have two figures here. We have this larger circle sector, and we have this smaller inner sector, circle sector. But those figures are similar. The one is just a scaled up version of the other. So in other words, if this arc length from B to C is S, we call it S units. So S represents the number that is the length of the arc BC. And if this distance here is some radius R, then this larger arc, because it's just a scaled up version of the arc S, is just going to be some some positive scalar multiple of S. So it's going to be equal to some real number scalar that's positive, K times S. And this larger radius here is just going to be K times the smaller radius. In other words, the larger sector, because it's similar to the smaller sector, is just a scaled up version of the other sector. And the thing that's useful about this is that for a given angle theta, if you take the ratio of this arc length Ks to Kr, it simplifies to S over R, which would be the ratio of this arc length S to this arc length R. So what it turns out to be is that for a given angle theta, the ratio of arc length to radius is a constant regardless the size of the circle. That's the key. You can increase or decrease the size of the circle that you're working on, but as long as theta is constant, the ratio of arc length, the distance that you sweep out through a central angle as you sweep around a circle, the ratio of arc length to radius is constant. And because it's constant, we're going to give it a name. We're going to call it a radian. We're going to say that a radian is just the ratio of the arc length that you've swept out divided by the radius of the circle that you're sweeping around. And it's customary to replace radian with theta as a representation of angle measure. So you'll frequently see this as theta equals S arc length over R. So again, S just represents the arc length as you sweep out around a circle. So this is actually a big definition in the world of trigonometry and is going to stick with you for the rest of your mathematics career. A radian, as a means of measuring an angle, is measured by taking the ratio of arc length swept out as you swing through the central angle, divided by the radius of the circle you're sweeping around. So what we want to be able to do is convert between angle measure in radian and degree measure. And here's the idea. We have a radian defined to be arc length S divided by radius, or I could spell it out, arc length divided by radius. This is how a radian is defined. And we could say, well, what angle in radians have we gone through if we rotate one full time around a circle of radius r? Well, if you go once around a circle, you get on this thing, you rotate all the way around it. Well, what is the arc length going to be? Well, the arc length is just going to be the circle circumference. And circumference is calculated by the formula 2 pi times radius. So the arc length is going to be 2 pi times radius. And the definition of radian says, hey, take the arc length and divide it by radius. So in radians, if you go one time around a circle, your arc length is going to be 2 pi r, the distance around a full circle, divided by the radius of the circle, but radius divided by radius will equal 1 as long as the radius is non-zero. And so you just get 2 pi. So what we see is that once around a circle, in radians, is 2 pi radians, which we can shorten to rad. But in degree measure, we know that that's 360 degrees. So now this gives us a way to convert between radians and degrees. We know that there are 2 pi radians per 360 degrees. Or we can write this relationship, we can write the reciprocal of this relationship. We can say, hey, there are 360 degrees per 2 pi radians. And this gives us a means to use dimensional or unit analysis to convert back and forth between degrees and radians. And the other thing to notice here is that the 360, you could divide it by the 2, so you would get a simpler relationship. It would say, hey, if you go 180 degrees, you only go, 2 goes into 360, 180, 2 goes into 2 once, 1 times pi is pi. Ooh, for every 180 degrees, you have pi radians. Or do it the other direction, and we get pi radians per 180 degrees. And all that's saying is that if you go 180 degrees, instead of going all the way around a circle, you only have gone halfway around the circle. So you wouldn't have gone the full circumference, you would have gone the circumference divided by 2. So you would just have gone pi r, you would have gone an arc length of pi r. A radian is defined as pi r divided by r, so you will have just gone pi radians if you go halfway around a circle. So we can use these relationships to convert between degrees and radians. And you don't really need to memorize them. It's really just, hey, the circumference of the circle divided by the radius of the circle gives you 2 pi radians. And once around a circle's 360 degrees, you can set up your relationship between degrees and radians. So for example, if we're going to convert 270 degrees into radians, we start with degrees, write down the measure that we have, 270 degrees, and then we multiply it by, we want radians as the result, so we're going to multiply by a ratio that has radians in the numerator and degrees in the denominator, so that degrees cancels with degrees, the units cancel. So we're going to say, hey, either 2 pi radians, which is once around a circle, or pi radians, which is halfway around a circle, divided by 180 degrees, which is halfway around a circle. So pi is equivalent to 180. So there's a sense in which this ratio is 1. your degrees cancel, the zeros cancel. 9 will go into 27, 3 times, and 9 will go into 18 twice, so we get 3 times pi divided by 270 is really over a 1, so it's 1 times 2. We get 3 pi over 2 radians. If we start with the radian measure, we have 5 pi over 6 radians. Now we need to multiply it by a relationship that has radians in the denominator so that radians cancel, and has degrees in the numerator so that degrees winds up being our answer. And again, we just write the relationship between radians and degrees. So we either go 2 pi, which is the circumference of a circle of radius 1 over 360, or we do 180 degrees per pi radians. The radians cancel. Pi divided by pi equals 1. 6 goes into 6 once. 6 goes into 18 3 times. That leaves us with 30 degrees. So we get 5 times 1 times 30 is 150 degrees. So one more example, 3 radians. We're starting with radians. We multiply by a relationship that has to have radians in the denominator and degrees in the numerator, and it is 180 degrees per pi radians. And pi isn't going to go nicely into 3, so we just multiply this out. We get 3 times 100 is 300, 3 times 80 is 240, so we get 100 plus 240 is 340 degrees over pi. The radians have canceled. This answers in degrees, and we could approximate it with our calculators by dividing the 340 divided by pi is about 108 degrees.